Welcome to Creative World. In this video, we will solve Chapter 2 exercise problem number 2.86. While solving this problem, we will be using Kirchoff's current law. According to this law, a cumulative current on a node inside an electrical network is always equal to 0. Sum of all entering currents on a node is always equal to sum of all leaving currents from that node. We also will be using Kirchoff's voltage law. According to this law, a cumulative supplied and dropped voltage across circuit elements in a closed loop is always equal to 0. Ohm's law will also be utilized while solving this problem. According to this law, voltage across any resistance R is always equal to the product of current through it and the value of resistance itself. Now move towards the problem. Exercise problem number 2.86. Find the value of voltage V1 in given below figure such that voltage VA is equal to 0. This is the circuit diagram of given problem. Inside this network, we have to find the value of voltage V1. One condition that is given in this scenario is voltage VA is equal to 0 volt. So without wasting time, let's proceed towards the solution. First of all, we will apply Kirchoff's voltage law inside this closed loop to calculate voltage across this 2 ohm resistance. For that purpose, we have to assume the direction of current. I am assuming the direction of current is clockwise, and according to this assumed direction, polarity notation across 2 ohm resistance is marked. Current entering terminal is taken with positive sign and current leaving terminal is taken with negative sign. Now write KVL equation for this closed loop. Start from VA. Current entering terminal is positive, so VA will be taken with positive sign. Next is voltage V1, current entering terminal is negative, so V1 will be taken with negative sign. Next is voltage across 2 ohm resistance V2 ohm will be taken with positive sign because current is entering from positive terminal. Now place the value of VA inside this equation. The equation will become 0 minus V1 plus V2 ohm is equal to 0. Here in this equation, V2 ohm is indicating voltage across this 2 ohm resistance. Place minus V1 on the other hand side of equal. The equation will become voltage across 2 ohm resistance will be equal to V1. Now apply Kirchoff's voltage law inside this closed loop. For that purpose, we have to assume the direction of current. Again, we are assuming the direction of current clockwise, and according to this assumed direction, polarity notation across this 4 ohm resistance is marked. Polarity notation across this 2 ohm resistance is already given in this scenario. Write KVL equation for this closed loop. Start from voltage across 4 ohm resistance that will be labeled as V4 ohm. This voltage will be taken with positive sign because current is entering from positive terminal. Next is voltage VA, current is entering from negative terminal, so VA will be taken with minus sign. Next is voltage of this voltage source, current entering terminal is negative, so 8 volt will be taken with minus sign. Now inside this equation, place the value of VA, that is 0 volt. The equation will become V4 ohm minus 0 minus 8 volt equal to 0. Place minus 8 volt on the other hand side of equal to calculate value of voltage across 4 ohm resistance, that will be 8 volt. Now apply Kirchoff's voltage law inside this closed loop. For that purpose, we have to assume the direction of current. I am assuming the direction of current clockwise. According to this assumed direction of current, we have marked polarity notation across these 2 resistances. In this case, voltage polarity notation across this 4 ohm resistance is not changed because voltage across it was 8 volt with this specified polarity. Write KVL equation for this closed loop. Start from here. Voltage across this 2 ohm resistance is equal to V1 because of parallel connection. Same voltage will be appearing across this 2 ohm resistance as well. So voltage across this 2 ohm resistance, that are V1, will be taken with positive sign because current is entering from positive terminal. Next is voltage across 4 ohm resistance, that is 8 volt, will be taken with negative sign because current is entering from negative terminal, minus 8 volt. Next is voltage across this 2 ohm resistance, that will be taken with positive sign because current is entering from positive terminal, and voltage across this 2 ohm resistance will be labeled as V2 ohm. Rearrange this equation to calculate voltage across this 2 ohm resistance, that will be equal to 8 volt minus V1. We have calculated voltage across this 2 ohm resistance, this 4 ohm resistance and this 2 ohm resistance. Now if we focus, it was given in this scenario that voltage VA that is appearing across 2 ohm resistance is 0 volt. And voltage across any resistance can be 0 in only that case whenever no current is flowing through that resistance. In this case, the value of VA0 means that no current is flowing through this 2 ohm resistance. In only that case, VA will be 0 because VA is the product of current I through this resistance and the value of resistance. Value of resistance is 2 ohm. So in order to make the value of VA 0, current through this resistance should be 0. And we know that the current is 0 in only that case when the circuit is open circuited. So we can say that this branch will be open circuited. That's why voltage across this 2 ohm resistance is 0 volt. And if this 2 ohm resistance is open circuited, it can be removed from the circuit. It will have no effect in the circuit. So we will modify the network by removing this 2 ohm resistance from the network and indicating all calculated voltage across these resistances. We have removed this 2 ohm resistance and voltage across these resistances with their polarities are mentioned in this figure as we have calculated in previous steps. If we remember, the directions of currents inside these 3 closed loops were clockwise direction. That's why we have taken these 3 currents labeled as I1, I2 and I3, and all of these are taken in clockwise direction. Now we have to calculate the value of current through this 2 ohm resistance, that will be equal to voltage across it divided by the value of resistance, V1 divided by 2 ohm. Similarly, current through this 4 ohm resistance will be calculated by dividing the value of voltage across it with the value of resistance. 8 volt divided by 4 ohm, it will become 2 ampere. And current through this 2 ohm resistance will be equal to 8 minus V1 divided by the value of resistance 2 ohm. Now we will apply Kirchoff's current law on this node. On this node, one current is entering while 2 currents are leaving. Entering current is I1. The value of I1 is equal to the value of current through this 2 ohm resistance because of series connection. And the value of I2 is 2 ampere, while the value of I3 is equal to the current through this 2 ohm resistance that we have calculated labeled as I3. KCL equation for this particular node will be I1 is entering current while I2 and I3 are leaving currents. So I1 will be equal to I2 plus I3. Place the values of currents inside this equation. I1 is equal to V1 divided by 2 ohm, while the value of I2 is 2 ampere and the value of I3 is 8 minus V1 divided by 2 ohm. Now in order to calculate the value of V1, we have to solve this equation. Multiply on both sides with 2. The equation will become V1 is equal to 4 plus 8 minus V1. Now place this minus V1 on the other hand side of equal and add 4 and 8 together. The equation will become V1 plus V1 equal to 12. Now add these both V1s together. The equation will become 2V1 equal to 12. Divide on both sides with 2 to calculate the value of V1, that will become 6 volt. So the value of V1 inside this network is 6 volt. This was exercise problem number 2.86. Thank you. See you again in next video.